Hi there. Today we're going to do an experiment and try and capture some light, the fastest thing in the universe. So, what is light? Well, light travels in straight lines and in the form of a wave. There we go. There's a wave there going up and down, up and down. And that's how light travels, but it travels in one direction. You can see by the red line, the red arrow there. The distance between the tops of the waves, or the bottom, is its wavelength. And that determines quite a bit, the colour of its light, the sort of light, and much more. The particle of light, what light is, a bit of light, is called a photon, the fastest thing in the universe. And here it is. There he goes. There's Captain Photon. He's in a bit of a rush because he's so fast. He's off again. And we're going to be trying to do an experiment to catch him. So there we go. Where's it come from? Light. Well, our natural light comes from the sun, and it travels through the vacuum of space at the speed of light. Nothing can go faster. It takes about 8 minutes 20 seconds for light to reach us, traveling almost 150 million kilometers in about 8 minutes. Now that's about 100 million miles, which is pretty far. So 8 minutes 20 seconds, it's going at quite a pace. There he goes. That's Captain Photon. If you look around you, if there's any daylight, 8 minutes 20 seconds ago, that light was in the sun. Now, different wavelengths of light give us different things. The very short wavelengths, you can see on the left, the wiggly line at the bottom, is radiation, gamma rays, X-rays, like that. Then the wavelengths get slightly further apart, and you get ultraviolet, you may have heard of, and infrared. And in the middle of that is the visible spectrum, ranging from violet to red, right the way through the rainbow of colours. Each of those colours have got a different wavelength. My eye detects them. Move further along to longer wavelengths, and you have infrared, which is heat, microwaves, and then radio waves, which is how you can hear a radio. So shorter wavelengths is a higher frequency, longer wavelengths is a lower frequency. It's very clever stuff. That's the electromagnetic radiation, electromagnetic spectrum. This is our eye. Ugh. Inside our eye, we detect light. We detect it on our retina, where there's 3 different cones, rods and cones, different cells that collect colour and black and white in our retina. Very clever stuff. Taken millions of years to evolve, and they're rather marvellous. Okay, we want you now, we're going to shut the blinds, and we are going to stare at a colour. Yeah? To see what happens. Stare at a point. So, in the middle of the image, we're going to show in a minute, there's a black dot. I want you to stare at that black dot, okay, for 10 seconds, and then we're going to change the picture. So, everybody stare without moving their eyes at the black dot in the middle. Keep staring. Keep on. Boom. That is a black and white picture. And it should be becoming black and white now. And what's happened is our eyes, the colours in our eyes get exhausted. And what's happened is we see the opposite colours. So we're going to try that again. Have a little look. 10 seconds. Keep staring at that dot. Okay, our retina's getting tired of the colours they're seeing. Keep staring at the dot, okay? And let's see if the opposite colours appear. Whoa! It looks like a colour picture, but in fact it's black and white. And that is our eye, the rhodopsin in our eye, getting tired and letting us see the opposite colour when we stop seeing it. It's all good stuff. Our skin's also got a chemical in it called melanin that goes dark when light hits it. So it's not just sort of in the eye and on our skin, but also different elements, different chemicals and different substances react to light, as we know, leaves as well. But so does silver. When it's hit by light, silver goes dark, which you may not know. When a photon hits a piece of silver, a molecule of silver, like this one here, hammering down from the sun, Captain Photon walloping into AgX. Ag is silver, X is a salt. Silver salt. And it wallops into the silver and becomes black metallic silver. Basically, it makes silver go black when light hits it. This discovery 170 years ago, getting on for 200 years ago now, enabled us to invent photography, which actually happened in Bristol, which is rather cool. Right, time to do some photon inhibiting. So we're going to do an experiment. The disappearing hand. Pretty spooky, but should be fun. I need you all to be very good. What you need to do is you'll all be given a piece of paper. When that paper's given to you, pretty quickly, you need to put your hands with your fingers pretty wide open on opposite sides of the photographic paper. That's what it is. One side of this paper has got silver on. You won't be able to see it, but it has. So the teacher's going to give out the bits of paper. And then what's going to happen, you're going to put your hands either side like this, holding onto the paper in the middle. And when you've got it held in there, don't move your hands away. You need to then do what the teacher says, which is go outside and then have a go, just keeping your hands together and see if you can get some photons hitting that paper. So just turn around a little bit, don't have to be very frantic, just basically let light hit the paper for a couple of minutes and then come back in and we'll see what happens.